Okay, in this one, we're going to talk about a specific type of reaction known as a precipitation reaction. Um, in a precipitation, and our goal here is, can we pick out a precipitation reaction and can we predict what the products are? So that's kind of where we're going from. We want to be able to uh, decide if something is a precipitation reaction. We want to be able to predict what the products are for a potential precipitation reaction. We want to know if a reaction happens, and we want to be able to write the net ionic equation. So there's a lot of stuff going on in here, but it's all related through precipitation. All right, we've already seen precipitation reactions in some other videos. I just want to point them out. This is what we talked about for our net ionic equation videos. Um, Here we had silver nitrate and sodium chloride made a silver chloride solid, and we have lead nitrate and lithium sulfate made a lead sulfate solid. These are both precipitation reactions because our guidelines, our rule here for precipitation reaction is you have to have solutions that react together and you have to form a solid product. So ionic aqueous makes ionic solid. That's a precipitation reaction. Ionic aqueous plus ionic solid, that's a precipitation reaction. Okay. The precipitate is the thing that is produced that is the solid. So in the first reaction, our precipitate is silver chloride. In the second one, it's lead sulfate. Okay. So, and we saw how to write the net ionic equations for these as we went through the net ionic video last time. Um, so what we're going to do in this one is I'm going to focus on how do we predict what the products are if we have a potential precipitation reaction. All right. The way we're going to do this is by doing what's called a metathesis or a double displacement. Okay. So what we're doing in this example is we're going to mix together potassium iodide with lead nitrate. So this is potassium iodide and this is lead nitrate. And so what happens when we do this is you have a flask of Ki and a flask of lead nitrate, and you mix them together. Okay. At the instant you mix them together, you have a collection of all of the ions together in solution. Okay. What we're going to do to predict the products is we're going to do a metathesis, which is an exchange of parts. Okay. We're going to take our collection of ions that we have and we're going to swap their partners. Okay. So what do we mean? Right, here's our generic example. If we have compound AB reacting with CD, then A and C, which are the cations, are going to swap spots. So here, potassium is paired with iodide first. It's going to get paired with nitrate. Lead was paired with nitrate first, so it's going to end up paired with iodide. So our products for this, right, we can think of it this way, right? Our Ki aqueous has dissociated into K plus and I minus, and our lead 2 nitrate has dissociated, this is aqueous, into lead 2 plus and NO3 minus. Yes, I know there's supposed to be 2 nitrates there. We're not going to worry about it at the moment because we're just figuring out what the compound should be. So one of our products is potassium paired with nitrate, and the other one of our products is lead paired with iodide. Okay. So the next thing we want to do is write what the formulas of these things are, right? So we have K plus, NO3 minus, so we get KNO3. And our other product is lead with I minus. So we have Pb, we have a 2 plus and a 1 minus, so we're going to need 2 iodides to balance that out. Okay, so those are the products of our reaction, potassium nitrate and lead iodide. What we're going to have to do is use our solubility guidelines to tell us if these things are soluble or insoluble. That'll give us the phase labels. Both potassium and nitrate are always soluble, so this dude has to be aqueous. Okay. We don't have a rule for lead, so it could be insoluble. Iodides are usually soluble, but lead is one of those exceptions where it's not going to be soluble, so this is solid, insoluble. Right? Soluble. insoluble. Okay. Since the lead 2 nitrate is insoluble, this is also going to be our precipitate. So we can identify what our precipitate is. Okay. Once we've done that, right, we can see now if we do this, right, potassium and nitrate have stayed in solution. Lead iodide has come out as a solid. So we can write it this way. That's what we just figured out. All right, this is a picture of what it looks like. You might have seen this in lab at this point too, that the lead iodide is this nice bright yellow solid that comes out right here. Okay. Um, so there we go. So what are we doing? Okay, we're there. Yeah, okay. Let's write the balanced chemical equation for this. Okay, that's what we need. Ki aqueous plus PbNO32 aqueous gives us, we already figured out this should be PbI2 solid and KNO3 aqueous. Okay, that's predicting the products. Now we need to balance it. We have 2 nitrates on the lead side, so we're going to need 2 KNO3s. That gives us 2 potassium, so we need 2 KIs. Gives us 2 iodides. We have 2 iodides in the lead iodide, so we're good. This is our equation. The lead iodide is our precipitate. Okay. Now the next thing we want to do when we have this equation is we want to write the net ionic equation for this. Okay. I'm going to show you 2 ways to do it. One way works for everything, and one way is just good for precipitation reactions. Okay. So we're going to use the same method we used before. Take your strong, remember, strong electrolytes that are aqueous are the only things that can dissociate. Okay. So look at this up. Ionic compound, aqueous, we can break it apart. So that's 2Ki aqueous plus 2I minus aqueous. Here we have ionic compound that's aqueous, that will break apart. Lead 2 plus aqueous plus 2 nitrate aqueous. There we go. Other side now. Lead iodide solid is going to stay together. PbI2 solid, because it's not aqueous, it can't break apart. And here we have the always soluble potassium nitrate. That is aqueous, and so we have 2K plus aqueous, 2NO3 minus aqueous. Okay. Now if we look at it, we find our spectators. Here's a spectator, and here's a spectator, right? Because we have 2 nitrates and 2 potassium. So these guys cancel each other out, which gives us our net ionic equation of 2I minus aqueous and a Pb2 plus aqueous to give us PbI2 solid. Okay, that's one way to do it. I think if this is the long way, this way always works. Okay, no matter what kind of reaction you have, this is going to work. If you know you have a precipitation, okay, if you know you have a precipitation and you can find the precipitate, right? Here's our precipitate, lead iodide. You can write the net ionic equation based off the precipitate. This is a shortcut method and you do not have to do it this way. But in the precipitation reaction, the precipitate is the only product. So you can start by writing the product. Okay. The other side are the ions that make up that product. So we have lead 2 plus and 2I minus aqueous. Okay. And this equation and this equation are the same thing. Oh, I shouldn't have said aqueous. I should say solid. Yell at me. -4, whatever. Okay. Now they're actually the same thing. Right? If you know you have a precipitate, just take your precipitate and break it apart, and that's your net ionic equation. Okay. The long way works every time. So if you want to do it that way every time, do it that way. Okay. You're not going to screw it up if you can break things apart correctly. All right. Let's look at another example. What do we got here? Barium chloride and aluminum nitrate are combined. We want to write a balanced chemical equation, write a net ionic equation, and figure out if a reaction actually happened. All right. Let's combine these. Barium chloride, BaCl2. We know that's in solution. It's reacting with aluminum nitrate. Aluminum has to be 3+, so we need 3 nitrates to go with it. That's also in solution. Okay. If it helps you when you're doing this, write the ions that are involved. Shit. Come on, man. Write the ions that are involved when you do this. Right? Barium chloride would dissociate into Ba2+ and Cl-. Aluminum nitrate should dissociate into aluminum 3+ and NO3-, and then pair them together. Okay, so one product should be barium with nitrate, and the other product should be aluminum with chloride, which means when we write our products, we should get barium with NO3-2. Oops, we'll figure out that in a minute. And then we're going to have aluminum Cl3. Okay. Next thing we want to do is balance this mamma jamma. What do we got? One aluminum and one barium is fine, but we have 3 nitrates and 2 nitrates, so we're going to need 3 of these, 2 of these. And we have 2 chlorides and 3 chlorides, so we're going to need 2 of these and 3 of these. Okay, gives us 6 chlorides and 6 nitrates, 2 aluminums and 3 bariums, and this dude is balanced. Okay, that's our balanced chemical equation. Okay, let's figure out what our phase labels should be. Okay, our phase labels, remember, look at our guidelines. Nitrates are always soluble, so this guy has to be aqueous. Chlorides are usually soluble. Aluminum is not an exception, so this is also aqueous. Now, look at this. We have something aqueous and we have something aqueous. Did we get a solid? No. No precipitate. So that means we got no reaction for this guy. Okay. We can still try to write a net ionic equation for it. This will help us figure out and prove to ourselves that we got no reaction. Okay. So 3 barium 2+ aqueous plus 6 chloride aqueous plus 2 aluminum 3+ aqueous plus 3 nitrate aqueous should give us 3 barium 2+ aqueous, 6 nitrate aqueous, 2 aluminum 3+, 3+ aqueous, and 6 chloride. I ran out of room. Aqueous. All right. Find your spectators and cancel them out. We got 3 barium on this side and 3 barium over here. We got 6 chlorides and 6 chlorides. We have 2 aluminums, 2 aluminums. We have 3 nitrates, which should really be 6 nitrates. Somebody should yell at me. It should be me because I'm by myself over here. 6 nitrates. And 6 nitrates. Look at this. Everything canceled out. This means no reaction. Okay, that's our official definition, right? If you know you're working with and trying to get a precipitation reaction, no precipitate is no reaction. Okay, if you're writing your net ionic equation and everything cancels out, that is no reaction. Okay, so this is kind of the official way, is that if everything cancels out of your net ionic equation, then that is no reaction. Okay. One more thing we're going to do, and that's a synthesis. And I always say this, if we can do it forwards, we should be able to do it backwards. Synthesis is doing the precipitation reaction backwards. It's where your goal is to make a specific compound. Okay. This is where you get to be a little bit creative. You don't have to be if you don't want to be, but you can be a little creative and we get to choose what our reactants are. Okay. So our example is going to be, let's make some solid manganese 3 sulfide. Okay. This is manganese 3 sulfide. How are we going to accomplish this? Well, figure out what ions we need to make this dude. We're going to need a cation and an anion. We're told this is manganese 3, so we can say this is manganese 3 plus. Sulfur is always 2 minus, so there we go. Manganese 3 sulfide is manganese 3 plus, and sulfide, which is the 2 minus. Then, once we have our ions picked out, pair them with an ion to make a compound that is soluble. Okay. One of the easiest ways to do this is just to pick an always soluble ion to pair with it. So for manganese, maybe I'll pair this with nitrate. Okay. Remember, this has to end up being aqueous. For sulfide, maybe I'm using lithium. Aqueous. There we go. Okay. Now we're well on our way. We have actually we have 3/4 of our reaction done, and we can write this out. Okay. Manganese NO3 aqueous plus lithium 3 sulfide aqueous. That's not the name. I'm just writing a formula and saying things as I go. All right. And we know we're going to make Mn2S3 solid. The other product is the crap that's left over. Okay. Which here, that's the ions you put in to make the compounds. So we added nitrate and we added lithium. So our crap that's left over is lithium nitrate. Okay. Our last step of this is to make sure this dude is balanced, right? Start with the most subscripts and the biggest subscripts. That's here, 2 manganese, 3 sulfurs. That gives us 6 lithiums and 6 nitrates. So we need 6 lithium nitrate. And this is your final answer for this question, right? What is our synthesis plan? We want to make this thing, and we can do that by reacting manganese 3 nitrate and lithium sulfide. Okay. Let me know if you have questions or need anything. I'm here for you to help. I will see you in class.